What is friction? Most of you know what friction is, but formally, friction is the resistance to motion of one object moving relative to another. But here's the thing. Let's say we have a magnifying glass and we zoom in right here. What does the surfaces really look like when you really zoom in at a microscopic level? Well, if you actually look at them, these surfaces are not smooth at all. They're very jagged and rough and irregular. And it's to the point where it's kind of like a mountain range, like two mountain ranges like kind of connected together, and they're kind of interlocked. So when you actually try to like move an object, you're basically rubbing mountain ranges past each other. Because think about like two bricks. Bricks are really rough, and if you grind them past each other, you can kind of look at the surfaces as really rough, and the surfaces are going past each other. Now, regarding friction, a common question I ask in a class is, why do sliding objects come to a stop? And almost immediately, all students will say, friction. And well, that's true, right? In the absence of friction, all objects will just keep moving forever. But we got to think about why that is true. Now, let's look at it in terms of energy. Now, moving objects have what we call kinetic energy. So kinetic is just a physics word meaning moving. So if you have an object that's moving, then it has kinetic energy. But if you think about two surfaces grinding past each other, right? Imagine trying to slide a brick along an asphalt road. It's going to come to a stop pretty quickly, because think about the surfaces. They're very both rough surfaces. And as they're grinding past each other, that takes energy, right? So as the surfaces grind past each other, they have to kind of like break bits and pieces off. So energy is lost in the process. So that energy is converted from kinetic energy to heat and sound, right? Because think about it. If you have a brick sliding down some road, you can definitely hear it. But imagine you had a hockey puck on an air table. Now, in the absence of the air sound, you couldn't hear it, right? If you can remove friction, you would not be able to hear things moving. Because why would they make sound? Because sound is caused by friction causing the parts and pieces, etc., to break off and smooth out the edges. Now, the brick will eventually come to a stop because it has lost all that energy to converting to heat and sound, etc. So that's a different way of looking why friction causes things to come to a stop, because basically the object loses energy in the process. Now, what's this? What is this very irregular, alien-looking like thing? It's actually an object in our everyday lives that you got to be careful with, because this actually is paper. This is the side of paper. So if you've ever gotten a paper cut, this is why paper cuts hurt. The side of paper is very ragged. So when you zoom into anything, so even the smoothest metal finish, it is irregular if you zoom in enough. So paper especially is actually really ragged once you get down to the microscopic level. And these fibers act as little, almost razors when they go against your skin. That's why a paper cut can hurt so much. Now, let's talk about the types of friction. So let's say we have a person pulling this crate. Now, again, the surfaces are really, really irregular between each other, right? And right now, you can kind of see how they're almost like interlocked and kind of intermix these surfaces. So you have these mountain ranges, as I like to call them, one up and one down, when they're interlocked. So as this person is trying to pull, nothing's happening, right? The person is pulling with a tension T with a rope, and there's a force of static friction. We call it static friction because the surfaces are not moving relative to each other. So now the person is going to try to pull harder. And take a look what happened. As the person's pulling harder, it takes more effort, there's more tension, and there's more static friction, right? Yet, it still does not move. So let's pull even harder. So take a look what's happening. There's more tension, but there's also more static friction. The forces are still balanced. That's the key here. That's why it's not moving yet. Now what's going to happen is this. You may have noticed this in like regular everyday life, that if you pull hard enough, eventually, hopefully, all of a sudden, it starts to move. And it actually feels easier once you get it moving to keep it moving. And that's not just perception, that's actually true. Now let's look at this as like friction versus time. So as you're pulling more and more and more, it takes more effort, right? So look at this. The effort meter is going up, so there's more and more friction, more and more tension, and it's still not moving. Right now, this is static friction. But you may have noticed this. All of a sudden, like nearly instantaneously, the object kind of gives a sudden jerk and starts to move. So, and this is true. The amount of friction decreases suddenly. The amount of tension that you need to pull decreases suddenly from some value down to a lower value. So let's look at this again. As you're pulling harder and harder, it's not moving, but the amount of friction is increasing as you're pulling harder and harder. You reach some maximum value, and then all of a sudden, with a jerk, it changes and starts to move nearly instantaneously. So this right here is static friction. And I want you to notice how the static friction can be any value from just above zero all the way up to some maximum value. Then nearly instantaneously it changes from static friction, that's when the surfaces are not moving, to kinetic friction. That's when the surfaces are moving relative to each other. And notice how the kinetic friction is generally just one value. So that's going to be true. Kinetic friction can only be generally one value, whereas static friction can be any value up to some maximum value. So to summarize this, static friction occurs when two surfaces are not moving relative to each other. The static friction can be any value up to some maximum value, whereas in kinetic friction occurs when two surfaces are moving relative to each other. The kinetic friction can be only one value that doesn't change. Let's look at these examples right here. We have pushing a gigantic crate, a car speeding up, a car slowing down. So if you're pushing a gigantic crate, and let's say it's not moving, right? So this person is pushing with all his might, yet it's not moving. Well, the crate has weight, mg down. The crate has a normal force on the crate from the ground. Now the person's pushing, so there's a normal force on the crate from the person, and the static friction is resisting motion. So it's not moving. All the forces are balanced. It's balanced up and down, and it's balanced in the x direction. So there's no net force, and the crate stays put, right? So the forces horizontally are balanced. Now the only way to get this crate going is to overcome the static frictional force by pushing hard enough. Then once it gets moving, it'll be easier to move. But until that point, that crate's going nowhere. Now, here's an unusual example, which you may find unusual: static friction of a car speeding up. Now think about this. If you have the tires on the road are not sliding on the road. They make contact with the road, they grip the road, and then it loses contact with the road, but they're never sliding. So think of it this way: the tires are pushing on the road, and the road is pushing the car forward. So in this case, the car is speeding up. Now the car has weight, of course. There is no force on the car from the road, and there's a static frictional force. So that's the force that we consider that's making the car accelerate. So the tires of the car are pushing on the road, and the road is pushing the car forward, and that force is the static frictional force. Now, if the car is slowing down, you still have weight, you still have normal force in the car from the road, but in this case, the static frictional force is in the opposite direction. So static frictional force can be very specific, right? So it's resisting motion for the first example, pushing the crate. But in the second example, it's actually the force that's accelerating the car. And in the third example, it's the force that's slowing the car down. Now, these examples, a car speeding up and a car slowing down, very similar to how a person is, when they're walking. So like when you're walking along the floor, you're pushing your shoe or sneaker is making contact with the floor, and the floor is applying a force forward, and that is the static frictional force. You could think about it. Your sneakers are not sliding on the floor, you're making contact. So while the sneaker is making contact on the floor, it's not sliding. So that's static friction. So static friction can be a little bit more complicated, but kinetic friction is actually pretty basic. It's really just sliding. Anything sliding is kinetic friction. So if we have a car sliding on ice, we have weight, normal force on the car from the road, and the kinetic frictional force, FFK, on the car from the road. And kinetic frictional force is the easier one because that's always in the opposite direction of motion. So if that car is slowing down, it's just going to be in the opposite direction of motion, and that's it. Now, we want to quantify the amount of friction, and we call that the coefficient of friction. So let's say we have a car. It's driving on dry pavement with brand new tires, but then for whatever reason enters a skid and slides. Now, let's say the kinetic frictional force is 8,000 newtons, and the normal force is 10,000 newtons. Well, the ratio between friction to normal force is 0.8, so 8,000 over 10,000 is 0.8. Now, we call that the coefficient of kinetic friction, and all it is a ratio. It's the ratio of the frictional force to the normal force. So that's a very common quantity in physics, the coefficient of friction. It just tells you how much friction there is relative to the normal force. Now, we have brand new tires here, and the pavement is dry, so that's a really good coefficient of friction. It could actually be even higher. But let's say we have old tires. Now, what's going to happen with old tires is going to decrease the amount of kinetic friction, right? If you have weaker tires, not weaker, but older tires, it's not gripping the road as well, so you're going to have less friction. So the coefficient of friction is only 0.5. So 0.5 means only 50%, 0.5, of the normal force. 50% of 10,000 is 5,000, so that's the coefficient of kinetic friction. And because of that, since you have less friction, your car is going to slide further than before. Now, if we go to the worst case scenario, we have a car and we have old tires and you're entering a patch of black ice. Now, the friction is going to be terrible. So you have less friction, so the coefficient of friction is only 0.10. So 10% of the normal force becomes friction. And since you have such little friction, that car is going to slide a very long distance, etc., etc. So this relationship here, the coefficient of friction, all it is a ratio of how much frictional force there is over normal force. And we commonly rewrite this in physics. So going back to the definitions here, if we actually solve it for friction, for both of these, you can see that frictional force is less than or equal to mu s n. So what that means is the frictional force can be any value equal to mu s times n, etc. But for kinetic friction, it's just equals because the kinetic friction is only one value. So I like to say that physics is F-U-N is fun. Now, so let's say the normal force is 10,000 and mu s is 0.7. So that means your maximum static friction would be 7,000. Now, let's say your kinetic friction is 0.4. So if your normal force is 10,000, 0.4 times 10,000, your kinetic frictional force is only 4,000. If we put it into this example, let's say a person is pushing a 100 kilogram crate for whatever reason, right? And let's say we know mu s is 0.85 and mu k is 0.6. How much force should the person push to just get the crate going? Well, we should draw a force diagram, and since we're running equations, we should define our direction. So the crate has weight. There's a normal force on the crate from the ground. The person is pushing. There's a normal force on the crate from the person. And there is a static frictional force on the crate from the ground. Now, the y direction, normal force minus weight equals 0. So therefore, the normal force is equal to the weight. So we can actually calculate how much normal force there is. 100 times 9.8, 980 newtons. So that's the normal force. Now, since we now know the normal force, we can now write the x direction. Now, the x direction is the normal force the person is pushing with minus the static friction equals 0. So in this case, the normal force is equal to the friction. So we're trying to find how much force should the person push with. So since that's equal to the friction, if we solve for the friction, we can figure out how hard the person should push with. Now, friction is also going to be mu s times n. So 0.85, so 85% of the normal force, 85% of 980 is 833. So the person needs to push with 833 newtons of force to get the crate going. And once the crate is going, it's just going to keep moving. Now, you don't need that much force to keep it going as to get it going. So if we look at this, it's pretty much the same example. You have weight, normal force, etc. But the difference is it's now kinetic frictional force. So the equations are very similar. You still have the same normal force on the crate from the ground. It's still 980. But the difference is if you now solve how much force the person should push with, it's only 60% of 980. So the person only needs to push with 588 newtons of force to keep it going. So that's friction, right? So to summarize all this, friction comes in two types. It comes in static friction when the surfaces are not moving relative to each other, and kinetic friction when they are moving relative to each other. And the coefficient of friction is just how much of the normal force becomes friction, and that's going to be a ratio. Now, usually in physics, I'm always very big about units because you kind of have to be, but you may notice that mu s and mu k don't have units because it's a ratio between the friction to the normal force. So it's newtons divided by newtons, so there is no unit. So that's it. So that is concepts of friction, and with that, that's the end.